And I would like to introduce our first speaker, Mr. Badri Younes, the Deputy Associate Administrator for the SCAD Network. Badri.
Thanks, Mike.
Well, good morning to all of you. I bring you the best wishes and the thanks of the NASA Administrator, Mr. Bolden, Charlie Bolden. He couldn't be with us today, but he would have wanted to be. But he had asked me to thank you all for being here. It's a partnership that we have between us and you. We do a lot of great things, but great things that are done, if not communicated, especially to the young folks and other people, will lose their value. So, on a day like this, as I spoke to some of you outside, and so some of my words may be repetitive, but it's the kind of partnership that we would like to build on, to get the message out, to sensitize the minds of the young generation to the importance of the work that NASA does, and the importance of NASA and working for NASA, and to stimulate their mind to pursue science and engineering and technology and mathematics as a career of choice. So I will be talking to you today about NASA Space Communication and Navigation Program, for which I'm responsible. And I'm the Deputy Associate Administrator. I work for a person by the name of Bill Gerstenmeyer, who oversees all of NASA's human exploration and operation. So, next chart. This is the kind of network that we have. 3 different networks that evolved over time, catering to a different set of customers from near Earth to deep space. And also, we have a space network that evolved out of the shuttle and the human exploration to provide near real-time support to anything that's in a near Earth environment below geo orbit. The deep space network is where you are at one of the facilities here, one of the stations. It caters to anything beyond geo, while the near Earth network caters to all of the science missions that primarily doing Earth science, going around the Earth in a very repetitive motion to study the Earth, from weather to all kind of missions with the objective to do Earth science observation. This is where we are going to. It's a notional architecture. We are charged of integrating all of these networks that have evolved independently over time into a single cohesive network of networks, providing transparent support to new classes of users that will be crisscrossing all of these boundaries, near Earth and deep space, in the future. So a network that caters to this class of user will require integrated capabilities, no discrimination, no differentiation between near Earth and deep space, except in what the laws of physics, tell us or establish. So we are trying to also introduce new capabilities. We are trying to leverage some old concept into future capability by building, instead of a single dish, to communicate, to provide the kind of energy and power to communicate with deep space mission, to have an array of smaller size antennas, so you can cater to many more users at the same time. You can close the link with someone who really operates in an austere environment with low energy level. So every station, and we have for the deep space network, we have 3 stations spaced by about 120 degrees, distributed around the globe, to have 24-hour and 7 days a week, visibility into our missions that are in deep space. We have one located here, one located in Madrid, Spain, and one in Canberra, Australia. They have evolved over time, as I said, catering to the individual need of specific missions. So there is plenty of redundancy in the type of hardware and the capabilities that they provide, driven primarily by the specific mission needs. The good folks at JPL, supported by their support contractors, are working very, very hard to harmonize across the entire network and to try to provide efficiency in the way we operate and trying to integrate the operation of the three networks under a single command instead of having 3 shifts per day at every station to follow the sun and have a shift per station controlling and managing the capabilities and the assets in the other stations. So we are also trying to introduce the concept of internet to TCP. We are moving it up into space, but TCP does not work in space because of the latency issue. So we are coming with a new concept for communication protocol called delay tolerant networking, DTN. You probably heard about it. It's being tested on the ground, pretty good for the battlefield and supporting networks on the move, ad hoc networking. Provide the kind of robust capacity that the actual physical capacity cannot support now. It can multiply that capacity into a much bigger virtual capacity. We are also introducing optical communication into our operation. Optical communication can provide 100 times the performance of an RF system, so it will allow us to either reduce the size of the communication payload on board the spacecraft, such that we can put more scientific instrument on board, or we can provide the kind of data rates that's needed to provide streaming video from Mars and from other planets. You all watched the MSL landing, and everyone had the question on their mind, wouldn't it have been great had we had streaming video coming down, from Mars? I promise you it will be possible, but not yet. Give us some time. So you have a roadmap how we are all evolving the capabilities. Definitely NASA doesn't get much in terms of a budget, although some people may think it's a lot, but really the kind of things that we do and the capabilities and the mission that we are trying to accomplish is not that cheap, and it returns a lot of dividends to the taxpayers. But with what we have, we are doing a lot. Many of the things that we do, we are really going to count on you in communicating to the ordinary folks, and hopefully through your messages we can also stimulate the mind and can make establish a new trend in the way young folk thinks. Instead of gaming and internet and other things, service-oriented kind of jobs, they can pursue science. We really need to revive that thing in all of their heart and their mind. Math and physics and all of these things are so critical to our growth, not just from a scientific perspective, but also from an economic perspective. So this is a timeline. I'm going to speed it up a little bit. Next chart. That's how we are going to evolve it. A mission that's going to the moon launching in 2013 that will provide us our first experience with the optical communication. And let's keep on moving. And by 2018, we'll have established that integrated network. And part of the thing that we are doing from an integrated network, since our budget is fixed, we are trying to introduce efficiency in the way we operate to generate enough funds to cover, to fund the new capabilities. And with the help of the people that you see around you from JPL and from ITT and from all of the NASA centers who are supporting our activities, we're able to save close to 40% of our existing funds. And with that 40%, we are building new, better antennas for deep space network. We are working on the space network infrastructure on the ground to introduce state-of-the-art, so we can get better return for our investment, and we can reduce the size, the cost of the transmission of a bit of information. And our target to reduce that cost by a factor of 100 still. And by 2025, the next chart will have evolved, and 23, next one, will have evolved, the deep space capability by building dedicated data relay network from around Mars, and that's when I promise you will get the streaming video. Before that, I will pursue targets of opportunity, because in order to house, first I need to produce the technology, and I have JPL is working it now, and we may have something by 2017, something that will allow us to get data rate on the order of 70 to 100 some megabit per second from Mars, which is great compared to what we are getting today, and compared to what we are getting now from Voyager that has crisscrossed the solar boundaries and provided a 70 bit per second. Remember the old days with the modem, the 4800 baud or whatever? No, now we are talking about gigabits. We are talking about trying to reduce the cost of communication by really packing more. And actually our requirements are also growing. In the past we used to be satisfied with very little, fewer bits of data, but now every file in the megabytes actually. So as our application and our requirement keep on increasing, we are trying to keep pace with that. In addition to that, our push toward optical will, is driven by the congestion that we are experiencing in the spectrum, the frequency spectrum, where we have so much contention from the commercial sector competing for frequencies that we are using now to support our operation. So by finding other means, we'll depend less and less on the lower frequency bands, and will make it possibly in the far future to commercial application. But we are working that with the regulation on how soon we introduce them in. Next chart. Again, this is a summary, what kind of capabilities we are expecting. A very integrated architecture with DTN as the basis for providing network-based services. And one of the requirements to have it to be internationally interoperable. So imagine yourself going on so many different trains, everyone going at different speed. It's going to be a challenge to get the international community to follow at the same speed as we are, because we have the intent, we have the people, we have the money, and we are proceeding. No guarantees with the others. But we are working very closely with them. And the future is going to involve more collaborative relationship among all space agencies to achieve more things in space. We can say that although NASA and other agencies may be able to accomplish this much out of their space program, but when we collaborate and we come together as a community of interest, we can achieve a lot more. And we are working on that. This is a planar view of our location around the globe. Again, these are color-coded. The red is to identify the deep space network. The green, the green color, they identify the near-Earth network that caters to polar orbit and satellite primarily. And we have station up at the North Pole as well as station at the South Pole. And they are wonderful places to visit. One of the challenges of my job is to visit every single site that we have. Boy, it's tough, But I got to see polar bears, and pretty soon I will get to see some penguins more. Hopefully, it's going to depend on the weather over there. In addition to that, I talked about the data relay network. We have satellites up in geostationary orbit, providing coverage to everything that's below that requires near real-time support. The color are coded in blue because all we need are, essentially you need one single station to have a view of the entire sky. But there is a small sliver of, an area at the other side of this station, completely at the other side, where you cannot see below a certain altitude. So we had to put another ground terminal up there. We put it in Guam. It's remotely operated out of the white sand and providing full coverage of the area underneath. And we supported the shuttle, we support the station, we support almost every single mission that NASA has, because even though we may not support data transmission, but we do the housekeeping, the command and control through this data relay system. On a single day, we are supporting over 100 missions, varying from human missions to suborbital all the way to deep space. And again, we are still supporting a mission that's going beyond our solar system. Next one. I already talked to the characteristics of of these networks, and these are the kind of missions they support. They are probably very familiar to many of you. Next chart. I already covered, the space in between the deep space networks. Goldstone, Canberra, it's in Tintinbilla in Australia, and in Madrid, Spain, and Robledos, the Chivalis. Next one. This is the DSN. These are the pictures of the various sites. They vary definitely, based on the real estate that you have. In some places we have very little real estate, so they are concentrated together. In other places they have the real estate. So with more real estate, we can do better science out of the infrastructure.